Okay, any questions before we get started? Okay, first of all, confession. I usually have your homework posted by now, so that I can talk about it. Unfortunately, I haven't been able to do this. This is, we're hot in the middle of letter writing season, and I'm writing a obscene number of letters. So I apologize for that. I do have your homework sixth graded. The grader's behind, so I'll get him to catch up, but we'll catch up on grading pretty soon. The next homework will be posted shortly after class. Any questions? Okay. Let me talk about this last theorem. I gave you this theorem. It was the second to the last thing I gave you. We passed on to a corollary. And we talked about one direction of this, but so you have a finite. No problem. If and only if is the correct product. Okay, so this was the last theorem that I had. And then we had a neat little corollary that if you have a nilpotent group that's finite and you have any integer that divides the order of that group, then there's a subgroup of that order. So why is this true? And this will also use, we've already done this direction. Remains to do this, and this will depend on the previous limit as well. Suppose let's suppose that G is a nilpotent group. Okay, and let P be if G is actually the whole CLOP subgroup, then you're done. And the reason you're done is because we already know that any P group is nilpotent, right? If not, then P is strictly contained in G. Therefore, P is strictly contained in G by previous limit. Remember, if you had a proper subgroup, nilpotent group, then that group is properly contained in its own normalizer. So also notice that the normalizer in G of the normalizer in G of P is itself. That is to say, this is its own normalizer. Now, why is this the case? Well, because notice that P the reason for this is, of course, P is a subgroup of its normalizer. And by definition, P is normal in its normalizer. So P is the only CLOP subgroup of the normalizer P. So if G and G normalizes, NGP, right? That is, if it fixes NGP, then G normalizes P. Because there's only one CeeLo P subgroup of the normalizer in G of P. So anything that normalizes everything in here also has to normalize that P CeeLo subgroup. Therefore, G is in the normalizer of G of P. So that's why that claim is true. So, so what can we conclude from this? Well, that the normalizer G of P must be on. So, in particular, each CeeLo P subgroup of G is normal. So, and let me point out that if P1, P2, Pn are distinct CeeLo P subgroups, then and so there's nothing that's in the IP CeeLo subgroup that's in the product of this, and this is because of normality. And G is the product of all these because, in fact, since the intersection of any of these is trivial, then the number of elements in the product of the CeeLo P subgroups is equal to G. Therefore, G is the direct product of the CeeLo P. Yeah, any questions on this? Yes.
I think I just missed where you went from. Then if the normalizer is the normalizer, then we can conclude that the normalizer is G.
Right. So, I should structure this, but let's see. If G equals P, then we're done. If not, right. So suppose that P is a proper subgroup, right? So we know that P is strictly contained in the normalizer of G of P by the previous limit, right? So we got that. And notice that the normalizer in G of P, when you take the normalizer of that, so this is stable under normalization, right? And so the normalizer actually, so what happens actually if the normalizer is less than G? It's a proper subgroup of G. So let me add this. Proper. Then normalize G of the normalizer in G, not the normalizer in G. That's again, an application of that one. Because the normalizer GFP is a proper subgroup, no of the other. Right? And so if you assume that this is a proper subgroup, then the normalizer of that group has to strictly contain the group itself. Right? So this is again that previous one. Is that clear?
Yeah.
Okay, so let me remind you of a fact that will be useful here. So here's a blast from the past. If it's a normal subgroup G, then remember what the condition is here. So if you have a normal subgroup G, then G mod n makes sense. This is a billion. Anybody remember a condition that gives you G mod n is a billion? If and only if n contains the commutator subgroup. Right? Okay. So we're going to not consider derived okay, so I'm going to start with G, and I think I'm going to call this G 0. Now, this contains its commutator subgroup, right? And in fact, I can even do that because the commutator subgroup is always normal. Now you've got a new group, the commutator subgroup. Start all over again. Take its commutator subgroup. And you can just keep doing this until you're blue in the face. Right? This is the derived series. You start with a group. There you have it. You take its commutator subgroup. Maybe that gets a little smaller. Now you got a new group. Take its commutator subgroup. Take its commutator subgroup. And keep going. Right? This is called the derived series. We say, follow the definition. Solvable. Yes. So you keep collapsing these things. There, because the identity is called solvable. Yes.
I just can't read what you have there. The G in commutator equals, and after that one.
This?
Yeah.
This is a G soup n plus 1.
Okay. I was like, okay. Thank you.
Yeah, I wrote that down because that's how you effectively define that.
I'm just blind. So.
Well, so am I. Which is part of the problem, I guess. So this is what we mean to have a solvable group. If you take its commutator subgroups enough, take this derived series, if you ever find yourself popped all the way down to the identity, this is solvable. How many of you have seen the definition of solvable before? Right. Is this the way you saw it? Because okay, so we're actually going to see another way that's equivalent to this in a moment, so let me give you an example. There we go. Any abelian proof is solvable. One step. Right, because if you have an abelian group, you take its commutator subgroup, you know. Let's go through this. Anybody know what the commutator subgroup D5 is? It should be the smallest normal subgroup G, D5, such that the quotient is abelian. Now, what normal subgroups D5 do you know? Well, the subgroup four, there's a bunch of subgroups four too, none of which are normal, right? But there is, notice that there's a subgroup of index two. So it has to be normal, right? Namely, in this case, it's the group of rotations, which is isomorphic to C5. Right, so big spin without the flips, that's a normal subgroup, right? And notice that D5 mod Z5 is actually isomorphic to Z2, which is abelian. So what I do know is that this thing is actually, since the quotient's abelian, I know that the commutator subgroup is a subgroup of it. The only subgroups of Z5 or Z5 in itself, and I'm sorry, so C5 in the identity, and when you mod D5 out by the identity, you don't get an abelian group. So there you go. So D5 is solvable. What if you have S5? Anybody want to venture a guess what the commutator subgroup is? Well, I don't know much, but I know the commutator subgroup has to be normal. So I have three choices: the identity, A5, and S5. Can't be the identity, right? Because S5 modulo of the identity is not abelian. And S5 is actually too much. S5 mod S5 is clearly abelian. The reason I know it's too much is because if I have S5 mod A5, I get Z2, right, which is abelian. There's the commutator subgroup. G2. What's the commutator subgroup of A5? That's right. Two choices. The identity, which it can't be because A5 is not abelian, and A5 itself. And now, at this juncture, I know that from a solvable standpoint, I'm totally hosed, right? Because all the future commutator subgroups that you're stuck, right? So this is not solvable. And this actually comes up later in the theory of equations. And we'll talk about this in 85% as well. So, So this is kind of a big one. Nilpotent implies solvable. By the way, is the converse true? Solvable imply nilpotent. You always got to ask those kind of questions, right? There's a counterexample on the board. D5. Can anybody tell me really? Okay, so for sure, I know that sucker's solvable because there I did it, right? But how do I know that it's not nilpotent? That is correct. The CeeLo subgroups of D5 look like Z5 and Z2, right? If D5 were a direct product of the CeeLo subgroups, it would be abelian. It would be isomorphic D10 or Z10, right? And so that is a good example of something that is, in fact, solvable, but not nilpotent. But this is kind of cool. Some P groups are solvable, abelian groups are solvable. Which nilpotent generalizes both of these. So let's go through this quick. Notice that if you look at CNG mod CN minus 1G, this is equal to the center of G mod CN minus 1G. And is abelian. Because after all, this is the center of something, so it's abelian. So what that means is this quotient here is abelian, which means that this thing must be contained in the commutator subgroup of ZNG. So I bet it's commutator subgroup contained in Zn minus 1G. For an arbitrary n greater than or equal to 1. And notice also for the end game that 1G commutator is equal to the commutator of again, ZG is abelian. Okay, so now that we've made that observation, let's point out that for some, and in since G nilpotent, some in CNG equals G. And so now we've got it because see if G minus CN minus 1G is ZNG 1G. G mod CNG. Abelian. So if you look at the successive commutator subgroups, what we have is the first commutator subgroup is in And G2 is in Zn minus 2G. And keep going with that all the way down, and you get GNC. Because this eventually collapses down to the identity and all the derived subgroups contained in this, and so you're good to go with that. Here is a very important, this is a very useful, I've used this actually theorem many times. This is one of the most, if you want to know if a group is solvable or not, and why would you want to know? Well, in fact, one of the applications is if you have a polynomial and you want to know if it's solvable for radicals, for example, you need to determine if your if the group is solvable, right? So this theorem is incredibly useful in this regard. Theorem. Number one, every, I'm just going this way. Yeah. Oh. Every subgroup and every quotient or homomorphic image of G solvable. So if you've got a solvable group, then every subgroup is solvable, and every G mod n is solvable. Every homomorphic image is solvable as well. And two, G is solvable. Well, this is very complicated. I'll say it this way. If n is normal in G and G mod n are both solvable, then G is solvable. This is really powerful because you have a normal subgroup of G, and you happen to know that it's solvable, and you also know that its quotient is solvable. The group itself is solvable. Right? So, I claim the new group 480 is solvable. So suppose you want to achieve number the number of CLO2 groups is 1 or 5, right? And the number of CLO5 groups is the divisor of 16. But it also has to be equivalent to 1 mod 5. So that eliminates this. So it's 1 or 16. I claim N2 or N5. One. One or the other is equal to 1. I'm going to make that claim. So let me establish the veracity of this. If N5 is 1, we're done. If not, then it's 16. Right? So 16 cyclic CO5 groups account for 16 times 4, which is 64 elements of 1 to 5. Right, okay. This leaves exactly forcing. Okay, so at this point, I've established one thing here. Either the CeLO 5 group is normal or the CeLO 2 group is normal. One of those two is happens. So case 1. N2 equals 1. So there is this unique CeLO 2 subgroup. We'll call it. Notice that so P is nilpotent plus salt. So, and also P is normal, which means mod P is isomorphic to C5, so is also salt. Therefore, is salt. Now, what if the situation reversed? Case 2, I suppose N5 is 1. So there exists a unique 5 subgroup of Q. And let's suppose that, and what's the order Q? 5, so Q is isomorphic to C5 and solvable. Also, Q is normal in G because it's unique, and the order of G mod Q is 16. So G mod Q is also solvable. Therefore, in this case as well, G is solvable. Questions on that? Let me go through a quick proof of theorem 449. Every subgroup and every quotient of the solvable group is solvable. Suppose G is solvable. Number 1, let H be a subgroup of G. Note notice it's pretty clear, isn't it, that any derived commutator subgroup of H is contained in the derived subcommutator G. So if G G, then H to that same. So whatever the solvable index of G is, that is how many times you've got to do this process to get the identity. H can be done that quickly, if not quicker. And number two, suppose is an onto homomorphism. So I'm doing this from the perspective of homomorphisms as opposed to quotients, but of course this is equivalent to G mod the kernel of F is isomorphic to H. So notice that in this case, F of GM is HM. So there you go. So homomorphic images are subgroups, solvable groups are solvable. How about this interesting part number 2 here that I just used on the groups of order 80? Now, remember, second statement here. Okay, so suppose n is normal of G, both n and G mod n are solvable. So consider function f G mod n as G mod n is solvable by hypothesis. There exists an n is equal to G mod n. And so, what does this mean? Well, this means that the derived subgroup right, because this goes to the identity. So that means whatever blob in here is has to be contained in the kernel of F, which is precisely n. Right, because the original map is just quotienting out by n. Right? And now this is solvable, right? So you solve. Okay. Any questions? Let me also point out, it should probably be noted that if you have a group that is simple and is not abelian, then that group is never solvable, right? Because what happens if it's simple and it's not abelian, then if you look at this commutator subgroup, it has to be all of itself, right? And so you're stuck. Actually, Here's a theorem. Called site constant theorem. Any this is a super cool theorem. If you have any group that's got odd order, it's automatically solvable. So if you've got something that's not solvable, we looked at some examples, A5, whatever, you will notice that they are always even. You guys, this is a cool theory. You want to see a quick proof of it? Yeah, so this is from Pacific Journal of Mathematics. This result, number 13, 1963. Issue number 13, I think. It is a 254-page proof. This is widely regarded as the longest proof of a single theorem in mathematical literature. Again, in fact, it is an entire issue in the Pacific Journal of Math. Those guys gave 254 pages, said, yes, we are going to publish our entire issue for this quarter or whatever they do on your one theorem. That is some good stuff right there. Anyway, so I won't be proving that in this course, but if you like, we could have a special topics course for to prove that too. Okay. Any questions?
A whole other PDF of the class about the same size.
Yeah, that's right. It's the thing about the group theory, a proof like this is there's lots and lots of intricate, delicate counting kind of arguments. And those can be very lengthy and kind of subtle sometimes. Normal series. Now, you said you'd seen solvability before. You probably saw it from this particular context, would be my guess. So, a chain of subgroups. Okay. Yeah. Such that notice that each such that every one up index is normal in the previous one. This is called a subnormal series. And I've always assumed, I guess, the reason it's called a subnormal series is because notice that G1 is normal in G0, G2 is normal in G1, G3 is normal in G2, and so forth. But there's no guarantee that, for example, G1 is normal. I'm sorry, G2 is normal in G, or G3 is normal in G. So the subnormal means you're only guaranteed normality with adjacency. The groups GI mod GI plus 1 are called factors. Because after all, you can take successive quotients, right? Because GI plus 1 is normally GI. And you call that quotient group a factor. It's a piece of data that you can get out of the series. And N is the length. And of course, since I'm calling N the length, you see why I want these containments to be strict, because I don't want to just sit here and repeat myself and be able to make any length I want. The series is normal. I've always sort of objected to you use the word series, but I really think it should be sequence, but whatever. The series is normal as opposed to subnormal if I is normal in G. Notice that this is a stronger condition because if GI is normal in G, then it's normal in GI plus 1 for sure. Example. For examples, if you have G GN is a normal series. Unless we got from it's a derived series, right? Because these are all commutative subgroups, right? It's a normal series. As is C1 G and G if G is not true. Let me give you another definition here. Sometimes if I have one of these normal or subnormal series, I might want to tweak it a little bit. Maybe it's too coarse and I want to make it finer. So we can follow the definition. Given the series, G0 contains G1. Gn. A one-term refinement is a series of the form zero, one, one. So notice what I've done is I've inserted a new group in the series where I have the appropriate thing where N is that's the big one, normal in GI. And yeah, plus one is normal at n. And a refinement, so this is a one-term refinement. As you might guess, a refinement is just a sequence of one-term refinements. So you get like a more general refinement, just add one term at a time and get a more general refinement. Okay, any questions on that? I think this is a good place to stop. The math club should be pretty interesting this week. There's an interesting, one of our grad students is talking, we'll talk about interesting problem number theory. I encourage y'all to be there. I will get the homework posted very soon. Any other questions? Any questions out there?
Is there any way we could get the homework due
Alright.
today extended?
Well, you all have a great weekend and I will see you by Monday.